All right, everyone, welcome. We're going to do a real quick vodcast to assist you guys with a little concept called limiting reagents. This is a concept in stoichiometry. A limiting reagent is a reactant that will run out on you, and if you think about a chemical reaction, you have to have the reactant. And if one of those reactants runs out, well, then the reaction itself is going to stop. So, for example, we have a really short warm-up here. And I'm just going to copy this over so that we can see it. Here we go. There, now I can read it. Okay. What is the balanced reaction between magnesium and oxygen? This is one of the best chemical reactions that we usually work with in the reactions lab. You guys remember the reactions lab, all the 5 different reactions that you guys were doing? All right, so the symbol for magnesium is Mg. Magnesium is a solid, and when you burn it, you are infusing it with oxygen gas. The product here would be magnesium oxide. It's a synthesis reaction. And we got kind of like a powdery substance at the end of that reaction. All right, so there's our balanced reaction. Remember, you can't do anything in stoichiometry without a balanced reaction. All right, your 2 starting materials. You'll always have 2 quantities given to you when you have a limiting reagent problem. So for the magnesium, we were supplied with 5.42 grams of magnesium. And for your oxygen, you were given 125 milliliters of this at STP. And remember, that is a gas. And you're being asked what is the maximum amount in grams of magnesium oxide that you can produce. All right, so typically on these limiting reagent problems, you're always going to be given 2 quantities, which means you have 2 setups to do. We are going to figure out with these 2 quantities just exactly how much magnesium oxide can be made with both of these quantities. All right, so here we go. Let's start with that 5.42 grams. 5.42 grams of magnesium. And we are going to do a traditional stoichiometry problem that's going to end us with mass of MgO. So there was some stuff that I showed you from last class to just kind of, just kind of visually help you guys out. I don't know if you need it anymore. I think some of you guys are starting to get the hang of it. But there's always this picture, this diagram to kind of help you out. Now, if you ever wanted to do this, and I think it's probably a smart idea, you can copy that into your notes and use it along the side while we're working through this problem. So just remember, the most important part is the mole-to-mole ratio, which comes from the balanced reaction. All right, so here we go. So we're starting with mass. We need to get to a mole-to-mole ratio, which means I'm automatically going to convert my mass to moles, so that I can do that. All right, the molar mass of magnesium is 24.3 grams, and that is per mole of magnesium. All right, now that I've converted my mass to moles, we can jump into a mole-to-mole ratio. So we're going to go from magnesium to magnesium oxide in this first problem. So what's the mole-to-mole ratio there between the 2? Look at your coefficients. Looks like it's a 2-to-2 ratio. So I like to label everything as I go to make sure that I don't cross-cancel with the wrong thing. So if I have magnesium on the top, I have to have magnesium down on the bottom. So I'm going to follow this, and I'm going to say 2 moles of magnesium because there's a coefficient of 2 in front of that magnesium. And I'm trying to go to magnesium oxide. So you see how I've already canceled moles of magnesium. Let's go to moles of magnesium oxide. In front of magnesium oxide, you have a coefficient of 2. All right, so now I'm on moles of magnesium oxide. Now, the point of the problem is we wanted to figure out the maximum grams of magnesium oxide. So you see how the only thing that is not crossed off right now is moles of MgO. Well, I'm going to make that mass of MgO, so I'm going to convert my moles to mass. All right, so use your periodic table to figure out the molar mass here. And you're going to want a calculator, so plan ahead, get your calculator ready. Let's see, so the molar mass of magnesium is 24.3, and oxygen is 16. Total molar mass here, I got 40.3. So 1 mole of MgO. Does anybody confirm that with me? Yeah, thanks. All right, is 40.3 grams. All right. Okay, so if the number's on the top, you multiply. If the number's on the bottom, you divide. Just real quick, I want to show you what you would type in on the calculator just to make sure you guys see this. So you're going from top to bottom here, which means you're going to divide. The 2 and the 2 cancel, so if you want to actually completely skip that part, you can. But I'm just going to let you know that here, moving upward, you would multiply by 2. Going down, you divide by 2. And then you're moving back up to the top over here. Remember, if it's on the top, you multiply, so we're going to multiply at the very end. So I'm going to take 5.42 divided by 24.3 times 2 divided by 2 times 40.3. All right, looks like over here I've got an answer of 8.988, so I'm going to give myself 3 sig figs. 8.99 grams is what I got for this one. Can anybody confirm that with me? Thanks, guys. All right. So there's one answer. The next answer, the next problem that we need to do is we're going to move from oxygen this time to magnesium oxide. So our starting material, very start of the problem, we're going to convert that 125 milliliters all the way over to grams of magnesium oxide. So there's our second problem. Let's get started. All right, so starting the second problem, 125 milliliters, again 125 milliliters of oxygen gas. All right, so you probably are thinking in your head about a conversion factor that will take you from volume to moles. What's that conversion factor again? Yeah, 22.4. What's the unit there, though? What's the unit? Liters is equal to 1 mole of gas at STP. So you have milliliters. You ready? We're going to do a quick conversion. Which one's smaller, milliliters or liters? Milliliters is small, liters is big. So there should be a lot of milliliters in a liter. How many? 1,000. Okay, if you still can't do that, try to work on those unit conversions. Okay, you're going to have that a lot. All right, let's keep going. So we're going to cross-cancel milliliters. There are 1,000 milliliters in a liter. So I'm going to put 1,000 on the bottom and 1 liter on the top. So I cross-cancel. All right, now I've got my liters. Now I can do that conversion with that 22.4. You ready? I'm going to put the 22.4 liters on the bottom. That's equivalent to 1 mole of O2. So I'm always cross-canceling. And notice how I like to label what it is. You see how I said O2? That's so I can keep track of my mole-to-mole ratios. All right, now that I'm on moles of oxygen, I can do my mole-to-mole ratio. What's the ratio between oxygen and magnesium oxide? 1 to 2. All right, we got to cross-cancel oxygen. So come back up. The coefficient in front of oxygen is nothing, so that means that there's a 1. All right, so down on the bottom here, I'm going to say there's 1 mole of O2 for every 2 moles of MgO. Okay, and those came from the coefficients. There's nothing here, so that's 1, and then there's a 2 in front of that guy. All right, so the heart of the stoichiometry problem is that mole-to-mole ratio. Okay, we're going to end the same way we ended the last problem, on mass. So we still want to try to convert that to mass, so we're going to do the same ending here. I'm going to cross-cancel this to make sure you guys remember that that's canceled. And we're going to change that mole of MgO into mass of MgO. 40.3 grams. All right. Okay, if it's on the top, you multiply. If it's on the bottom, you divide. So I'm going to start with that 125. Divide it by 1,000. Divide it again by 22.4. Times it by 2. And then times it by 40.3. Oh man, I got a really low quantity. Let's see, I'm going to go for 3 sig figs. 0.4. Looks like it's going to be 50 grams, if you round correctly. Nice. All right, so I'm going to zoom out a little bit so you can see this better. Oops. All right, so check this out. In a limiting reagent problem, you're going to have 2 answers, but only one of them represents the maximum that you could make. Do you recognize which one is the maximum we can make? What is the maximum we can make, guys? The smaller quantity is the maximum you can make. So we could only make 0.450 grams. Why? What's going to happen? Yeah, do you see that? You're going to run out of one of these reactants. You're going to run out of oxygen. This is your limiting reagent right there. So that was the next question on number 3 for your warm-up. Your oxygen right here is what we call your limiting reagent. This is the reactant that ran out. Okay, so just vocab check, okay? This is the reactant that ran out. And once one of those reactants runs out, the whole reaction will stop. It can't proceed because it doesn't have what it needs. It ran out of oxygen, so it'll stop burning. All right, that means we have a ton of magnesium left over that is unburnt, unreacted. Now, did we use some of that 5.42 grams? Did we use a little bit of it? Sure we did, because we have a small mass. This is the maximum amount of magnesium oxide that we can produce. So with that information, we can actually figure out, based off of the maximum amount, our theoretical yield. This is the maximum we can make. Sorry, I'm doing a vocab check. This is also called our theoretical yield, so maybe do a little vocab check here. Theoretical yield is sometimes called, is known as the maximum you can make. Max you can make. Alright, so take those notes, that's always good. Alright, so we can figure out, based off of our maximum theoretical yield, we can figure out how much magnesium is in there. You could figure out how much this substance, this product right here, how much magnesium was used to make that. And we can do that. There's a couple different ways that you can actually do that. Some students have used percent composition. Do you guys remember learning percent composition a way long time ago? There's a certain percentage of that compound that is magnesium, and you can do your math that way. But I'm going to show you one additional way that you could think your way through this. We know that in that 0.450 grams, there's a certain amount of magnesium in there. And you can either use percent composition, or you can do it my way. And I'm going to show you my way real quick, okay? So what we're going to do is we're going to figure out how much magnesium is in that product. Are you ready? Follow my thought process, because we did not use all of the 5.42 grams that was available to us, okay? We only used part of that. Here we go. I'm going to start with my 0.450 grams of MgO, and watch this. Oh dear. You can do stoichiometry to figure out how much magnesium was in that product. Let me show you how it works. You've already figured out the molar mass of magnesium oxide. Basically what I'm doing, guys, is I'm going to set up a stoichiometry problem to work my way from magnesium oxide all the way back to, guess what? Magnesium. To the mass of magnesium. You can use stoichiometry kind of for percent composition. You can do that, which is kind of neat. So you guys want to see it? Alright, let me show you how it goes. I already did the molar mass of magnesium oxide. It's right there in the previous problem. That's what I love about going backwards. You already have all of your masses figured out. The coefficient in front of magnesium oxide, yeah? Got a question real quick. Yeah, we're always cross-canceling. Grams, grams. Yeah. So you see how I'm on MgO? Guess what I'm going to go to? Mg. Yeah, because I'm on moles now, so I'm going to do my mole to mole ratio. So check this out. There was a coefficient of 2 in front of the MgO, so I'm going to go right here and say 2 mole MgO. And remember, I'm trying to go to magnesium. Do you remember what the coefficient was in front of magnesium? I think it was a 2. 2 mole of Mg. And then the very end, I'm going to end. See, I'm cross-canceling again. I'm going to end with magnesium. So check it out. 1 mole of Mg is, if you check, 24.3 grams. Okay, believe it or not, this will do the same effect as percent composition would have. Same thing. Notice I didn't have to figure out what the percent composition was. I didn't have to do that math. All I did is I set up a problem working backwards using stoichiometry. So this is actually a little faster than doing percent composition and looking at the compound and figuring out, okay, how much percent is magnesium? How much percent is oxygen? Okay, well, let me do that math. But you see, you end in the same thing. That's the beauty of stoichiometry. You can either use stoichiometry or you can do your percent composition. It doesn't matter. But this way, for me, is how I prefer to work my problems. All right, it's whatever you prefer. I don't like to sit there and try to go through, I've got to get my percent of magnesium in magnesium oxide. All right, you ready? So let's see. 0.45 divided by 40.3 times 24.3. All right, I'm using 3 sig figs, so I'm going to try to keep that consistent. I've got 0.271 grams. Do you guys concur with that? Anybody check that? Good, thank you. So, this is how much magnesium was in that mass. That's how much magnesium it took to make that product. So we had a lot of magnesium available to us. We had, starting the problem off, we had 5.42 grams available. So hold on. Let's see if we got your thought process going. We had 5.42 grams of magnesium available. How much did we actually use? We only used 0.271 grams used. So the last question that they gave you was, how much leftover will there be of the excess reactant when the reaction stops? How do you think you're going to solve that? Just subtract. All right, because of our sig figs and we're subtracting, you should probably only end with 2 decimal points. So I'm going to take that 5.42 and I'm going to subtract 0.271. And the correct answer on the calculator is 5.149. But what did I just say I'm going to do? When you subtract, it's not about sig figs, it's about decimal places, right? The least number of decimal places is 2, so how should I round my final answer? 5.15 grams of magnesium will be left over. Final answer. All right, so now we are pulling out the micro rocket lab that we did last class, and we're going to take a look at a couple of the questions down towards the end. Now, first of all, the thing that you need to know is that if you were absent, the class data has been posted on the class website. All right. There's one class that is missing, 6th period. So if you are in 6th period, could you email me the class averages, because I never took a picture and I didn't post it. So hook me up, okay? All right, but anyway, let's take a look at this. So we should have all of our averages up here. Number 1, why did pure H2 and O2 produce a 0 pop test? Now for us, we actually discussed this as a class last time. The hydrogen, the pure hydrogen, actually did have a little bit of a pop for most of my classes. And we tried to think about why that would be. And what was the reason? Why? Why did we get a small pop on that? Go ahead. Yeah, we have an oxygen-rich environment, so it kind of is logical that some of that oxygen is going to sneak its way into your rocket and give you some false pop tests. But is that what should happen in a pure hydrogen environment? No. Remember, you have to have both of your reactants to make a product, right? So anyway, if it did produce a sound, try to explain that. Hint, error, so we just talked about that right there, okay? Make sure that these answers are, thorough, complete sentence structure, that type of thing. All right, question number 2, we already did in class. That was the production of water, and it should be balanced. Okay, question number 3. Using your balance equation in 3 for the hydrogen to oxygen ratio, indicate which reactant, H2 or O2, was left over and how much of it was left over. And I said that the second one was done for you. So I'm going to help you out a little bit with figuring out part of this. I'm not going to do all of it, but I will do part of it, okay? So I'm going to come back over here, and let's check out some of these real quick. And let me just zip up that. Okay, it doesn't look very pretty, but I can help you guys out on the side. All right, so H2 to O2 is, let's do this one. Let's do this ratio. Let's pretend I gave you guys 5 parts, and, we're using parts, but what do you think I can exchange the word parts for? Moles. Good job. So we have 5 parts H2 versus 1 part O2. And we're going to figure out which one is in excess and how much is excess. All right, this is like a limiting reagent problem. So for this one, you just need to remember that the heart of stoichiometry comes from what? What's the heart of stoichiometry? Mole to mole ratio from the balanced equation, right? So you can't do any math without looking at the balanced reaction. So we're going to look at the balanced reaction here. Okay, there you go. and this was a gas. And you know, your water, if you said liquid, I would totally get it because, you know, it is liquid water. But if you said gas, that's actually correct. It was an exothermic reaction, and the heat turned your water back into a gaseous form. So just saying, don't have to put gas if you don't want to. All right, so let's look at these ratios, and you guys, I need you guys to recognize that this is just like what I just showed you. This is a limiting reagent problem. You have two quantities, so guess what I'm going to do? I'm going to show you two problems. And instead of parts, I hope you know that that's kind of like moles. So I'm going to change these right now to say moles. And I'm going to show you how I think my way through the problem. Yes, dimensional analysis. You ready? Okay. So from the reaction here, I'm going to go from hydrogen to water to figure out the maximum amount of water that this 5 moles of hydrogen could produce. You ready? So I'm going to come down here. I'm going to put 2 moles of H2. I'm looking at the coefficients here. To 2 mole of H2O. All right, so what is 5 times 2 divided by 2? 5. Am I right? Okay, let's go to the oxygen ratio. Oxygen, now I'm coming here and I'm doing this one. For oxygen, it's 1 part oxygen to 2 parts or moles of water. All right, 1 times 2 divided by 1 is 2. All right, everyone, what is the maximum amount of water that this ratio could produce? Maximum amount of water would be 2 parts H2O. That's the maximum we can make. So what that means, use your logic, what that means is that all the oxygen is gone. This is your limiting reagent. You use some of this hydrogen to make that 2 parts of water, but you didn't use all of it, did you? All right, so let's have a logical conversation. Some of you guys might be ready for this, not showing my work and just showing you and explaining how I figured out the excess. Are you ready? So I'm going to use a nice bright color here. So I know in this ratio that I produced a maximum of 2 waters. If I produced a maximum of 2 waters, I used some hydrogen to do that, right? But I didn't use all of the 5 parts, I only used some of it. If I made 2 here, come back, how much hydrogen did it take to make those 2 parts of water? How many parts would it take? If you made 2 parts of water, think backwards. How much hydrogen did it take to make that? How much hydrogen did it take to make that, guys? All 5 parts? No. How many parts did it take? 2. It took 2 parts to do that. Did I use all of my 5 parts? No. How many did I actually use? Only 2. So guys, how much is left over here? 3. And so if you come back, that's the logic of that answer. Okay, that's the logic of the answer here, the 3. There are 3 parts hydrogen left over. We had 5 available, but I only used 2. So there are 3 parts left over. Okay, now I'm going to show you one more just to make sure you got it. Okay, my favorite one, so you guys, by the way, for this one right here, for the 4 to 2 right here, was there anything left over at all? This one right here, was there anything left over right there? Nope. So it should be nothing left over, no excess. It was a perfect ratio. So I'm going to show you the next one over, the 3 to 3. This is not a perfect ratio. This is not going to work perfectly. You will have some excess left over. So let's figure out which one's an excess. So we have 3 parts hydrogen, 3 parts oxygen. Let's see what that one will look like. All right, so again, 3 parts hydrogen to 3 parts oxygen. Okay, remember the balance reaction looks like this. All right, those parts are just like moles. They work in the same way. Ready? For hydrogen, takes 2 moles or 2 parts hydrogen to make 2 parts of water. So that's easy, that's 3. Okay, now let's do this one. For oxygen, 1 mole or 1 part of O2 is going to give you 2 parts or 2 moles of H2O. You see how I'm interchanging those? I want to make sure you know that parts and moles are the same thing. All right, what's 3 times 2, guys? 6. Ooh. So, ladies and gentlemen, what is the maximum amount of water that we can produce this time with the 3-to-3 ratio? 3 parts water. Now, this one might take you guys a little longer to think through. That means the hydrogen's gone, so what's in excess this time? O2. Did we use all of the 3 parts? No. Did we use some of it? Yes. All right, so let's get some logic going. You were capable of making 3 waters. The coefficient here originally was a 2. How do you go from 2 to 3? What do you think you have to do there? How do you go from 2 to 3? Think about a multiplier. What's the multiplier? How do you go from 2 to 3, guys? 1.5. Okay, so we're going to multiply this by, if you take the number 2 and you multiply by 1.5, you will get 3. Okay? That's my logic there. Multiply by 1.5. All right, you guys, so we have some oxygen left over. Let's go do that. You ready? If you made 3 waters by multiplying by 1.5, come to your oxygen. How much oxygen did it take to make your 3 parts of water? There's originally a 1. What do you think I'm going to do here? 1.5. So I only use 1.5 of my oxygen. How much oxygen did I have available? 3. So if I only used 1.5 and there was 3 available, how much is left over, everyone? 1.5 is left over. All right, ladies and gentlemen, I'm not going to help you with the remainder. I hope that helped you a little bit. Make sure you do your post-lab questions right underneath here according to the class data. Make sure you look at the class data. It says, why was that mixture the most explosive? Please consider the answer to question number 4 right above there. And then what do you think could you do to make your rocket actually go fly farther? Not make a louder pop, but actually fly farther. So consider that one. There's a bunch of different answers that are acceptable. And then why didn't the hydrogen and oxygen gas react immediately when you mixed them, guys? Why didn't they react? Why didn't they react? There wasn't a spark, that's right. So sometimes we call that an activation energy to make the reaction work, to make the reaction go. So remember, you usually have to put some energy in to a reaction to make it go. All right, so anyway, I'm going to cut it off here, and after this we're going to get ready for our quiz. So take a minute to finish up your lab, turn it in, and then we will get that quiz started. Adios, guys.